So with that, let's start talking about inner coordinates. All right, we have these models for the eddy diffusivity, the epsilon m. We have models, but if you look at the models, you can see something kind of interesting. They're not expressed in terms of x, y, u, whatever. They're expressed in terms of something else, y plus, or u plus, or v plus. So how do we, what are those things, and how do we actually get our current model into those, the forms there? So it turns out that these things are called inner coordinates, so y plus, let's see what else, u plus. These are called the inner coordinates. Inner coordinates are a representation or sort of a normalization of the coordinate system based on certain things we actually care about in the fluid flow. So for example, in turbulent flow, we might care about the boundary layer thickness, like the viscous sublayer thickness. We might care about the size of the eddies that are occurring in the flow. So we don't want to, just like when we went through the normalization process in the correlation discussion, here we want to normalize by something that's going to be generalizable for a bunch of different flow configurations. So here we have u plus, y plus. Let's talk a little bit about how to get to those things. Right, and pointing out here, I guess this was just to point out that we know that the things that are important here are fluctuation, or the fluctuations in u and v. And if we remember, right, u prime is going to be approximately the same as, oops, v, not y. U prime is approximately the same as v prime. Those fluctuations are about the same. What else can we see here? Yeah, let's leave it there. So let's figure out how to get these inner coordinates. It's really not that, it maybe sounds scary, but it's really not that bad. So we have inner coordinates. Here's a definition. Inner coordinates are obtained by normalizing with scales that are most important for turbulent flow, as we've said. So let's start with the length scale. All right, so our length scale, we're going to say that this is going to be the approximate size of the viscous sublayer. All right, this gives us our inner position. Inner position, and that is y plus, and that's going to be the actual y coordinate divided by some characteristic length L characteristic viscous sublayer. So first of all, why do we pick the viscous sublayer as the normalizing length scale? Why not pick the full turbulent boundary layer thickness? And think about what in a heat transfer problem, what in even a momentum transfer problem for turbulent flow, what is important there? Where's all the heat transfer resistance in that flow? It's in the sublayer, right? So we normalize based on that because that's what's important for the flow. So that's our inner position. We are ultimately going to have to estimate that L characteristic, and we'll do it based on eddy size. But for now, this is the definition of this. So the second thing we want is a velocity scale. Okay, and velocity scale is going to be the approximate size of the velocity fluctuations. Okay, so velocity fluctuations are denoted with this symbol U star, U asterisk, whatever you want to have. So the size of those fluctuations is given by that, that character U star, and that's going to be our normalizing thing for velocity. So we'll say our inner velocity is U plus, which is equal to U bar over U star. Right, and again, like U bar is going to be a function of Y. U plus is going to be a function of Y. U star may be a function of Y as well, which we'll see. Okay, last thing is going to be on the energy side, we have the temperature scale. Okay, so temperature scale is approximate size of the temperature fluctuations. Okay, and that is denoted, the temperature fluctuations are denoted T star. So then our inner temperature inner temperature is, well, we don't want necessarily T plus, right? Because when we're talking about temperatures, we always want to normalize the temperature as the temperature with respect to some reference temperature, so that we could do this in Celsius or Rankine or whatever we want to do it in. So our inner temperature is going to be theta plus. And so theta plus is going to just be T, let's say TS is our reference temperature. That's the temperature of the surface. TS minus T bar divided by T star. All right, so we now have inner position, inner velocity, inner temperature. You're going to see these things cropping up, but you just have to keep in mind they're just representations of the position in the flow or in the velocity or whatever, or the temperature with respect to something that we care about for turbulent flow, which is characteristic or average viscous sublayer thickness. It's the fluctuation size. Okay. So our next job is let's estimate how big these things are. How big is the viscous sublayer? How big are these velocity fluctuations?